Now look at this question. If 2a plus 3b plus 6c equal to 0, then show that this function ax square plus bx plus c has got one root. This equation has got one root between 0 to 1, right? So it has got one root between 0 to 1. See, actually we will apply in such a cases, we will be applying the rolle theorem on the integral of this, right? On the integral of ax square plus bx plus c. If that satisfies rolle theorem between 0 to 1, then this will have a root, right? So let's consider a function fx equals to ax cubed by 3 plus cx, right? Let's apply it over here. Now see, at x equals to 0 your function is 0. At x equals to 1 you have f1 is a by 3 b by 2 plus c, which is 2a plus 3b plus 6c, right? And that's 0. So you see the function is polynomial function. So polynomial functions are continuous. It's also differentiable. So it is continuous between 0 to 1 on the closed interval 0 to 1. It is differentiable in the open interval 0 to 1, and f0 is f1. So all the condition of rolle theorems is satisfied. So it means from 0 to 1 there will be at least one root, there will be at least one real number c such that f dash c is 0, or there will be at least one root of this equation, right? So this is how this problem can be solved using Rolle's theorem. I'll go for the next question. It's a very similar question. Here we have to prove that this has got a root. This equation has got a root between 0 to 1. So I'll apply Rolle's theorem on the integral of this function, on the integral of this expression. So I'll consider here the function fx equals to a naught xn plus 1 upon n plus 1, a1 xn upon n, right, plus an1 x square upon 2 anx, right? This is the function. This is the function. Now you can see yourself over here that this function is a polynomial function. So it will be obviously continuous in the open interval from 0 to 1. It will also be differentiable it will be continuous in the closed interval 0 to 1. It will be differentiable in the open interval 0 to 1. And also see, f0 will come as 0 and f1 will be a naught upon n plus 1 and plus an, which is coming out of 0. So you have f0 equal to f1 also. So all the three conditions of Rolle theorem is satisfied. So obviously this function, the derivative of this function f dash x, which is obviously a naught xn plus a1 xn minus 1 plus an minus 1 x plus an. This will have a root between 0 to 1. This will certainly have a root, at least one real root. You will have at least one real root between 0 to 1. Alright. So I'll go for the next question again. See this question. If f phi and psi are continuous on closed interval a to b and derivable on open interval a to b, then show that there is a value c lying between a and b such that this determinant is 0. For proving this, let me choose a function and apply Rolle theorem. Let the function is gx, and this is fa FB fx. This is phi A, phi B, phi x, and this can be psi A, psi B, and psi x. Let's choose this function. Now it will be a polynomial, it will be a function which will be involving f psi, f phi and psi. It will be involving a function f phi and psi. Since f phi and psi all are continuous and derivable, continuous on closed interval a to b and derivable between a to b in open interval, so I can expect gx also to be continuous on a to b, because gx will be a function which will involve fx, phi x and psi x with some constant coefficients, right? It will be a combination of fx, phi x and psi x. It will be a linear combination, you can say, of fx, phi x and psi x. So if fx, phi x and psi x is a continuous function, then any linear combination of fx, phi x and psi x will also be a continuous function. Same is true for derivability also. Since these functions are derivable in open interval a to b, so any linear combination of these functions will also be continuous and will also be derivable on the open interval a to b. Now let's check the other condition, the last condition, that is ZA. Sorry, let's check at that GA. What is the value at A? GA is going to be how much? Fx, Fa, FB, Fa. This will be phi A, phi B, phi A, and this becomes psi A, psi B, and psi A. So this is, say, the two columns are equal. When the two columns are equal, the determinants are 0. When I put x equal to b, then this column will be equal. Then also determinant is 0. So you see, all the conditions of rolle theorem are satisfied. So the derivative of g dash x, which will be of course fa, fb and f dash x, phi a, phi b and phi dash x, psi a, psi b and psi dash x at one value, at least they will lie at least one real number between a and b, such that g dash xc is 0, and that will give you this expression, right? So at least there will be one real number c between a and b, such that this function g dash x will be 0. All right, consider this question. Here we have to prove that between any two real roots of ex sin x equal to 1, there is at least one real root of ex cos x plus 1 equal to 0. This is very famous question, right? So here, in order to prove this, I'll consider a function e to the power minus x minus sin x. Let this be the function. So if you have, say, first of all, this function is continuous. It is continuous on the real axis. This is also derivable. Sine trigonometric functions are derivable, continuous as well. Exponential functions also continuous. The graph of e to the power minus x goes like this, right? Sin x is like this. They all are continuous. So difference of a continuous function will also be continuous. So f is continuous on any real axis. It is x is continuous on fx is continuous, fx is derivable also. Now consider two roots, alpha and beta. Let's consider two roots, alpha and beta, so that e alpha sin alpha is 1, e beta sin beta is 1. this can be written as e to the power minus alpha minus sin alpha equal to 0, and e to the power minus beta is 0. So you find that alpha and beta are the root of this equation as well. It means f alpha and f beta both are 0. Alpha and beta are two roots of this function, two roots of this equation. So you find f alpha and f beta both are 0, and also fx is continuous between alpha to beta. Fx is continuous, I can write, is continuous on closed interval alpha to beta, like this, is derivable on open interval alpha beta. So, and also f alpha and f beta are 0. So all the three conditions are satisfied. So there will exist at least one real number between alpha and beta such that f dash c is 0. That will give you minus e to the power minus c minus cos c equal to 0. Or I can write e minus c plus cos c is 0. Or I can write ec cos c plus 1 equal to 0. Right? Or you can say there exists a root of, between alpha and beta, there will exist a root of this equation. Right? So it's a very famous question. There exists one root, there will exist at least one c between alpha and beta such that this equation, that is the root of this equation, at least one root between alpha and beta. This equation at least one root between alpha and beta. That's